Thank you. I must say, I remember the days, and that was not long ago, where 500 people in a CVPR conference was considered a big success. So now we have 3,600, my God. So I'll be talking about autonomous driving from the perspective of Mobileye. This is why you see the Mobileye logo on all the slides. And it's not going to be the kind of talk that I'll tell you how things are done. I'll tell you something more interesting is what are the things that needs to be done. I always tell my students that 80% of the work is knowing what to solve. The remaining 20%, if you don't do it, somebody else can do it. It's not that of an issue. Knowing what to solve is really the big thing. So we'll talk about autonomous driving, and it's all about computer vision, machine learning, reinforcement learning, all the good stuff that we're all doing here. And you'll see what kind of a big impact it's already having, but is going to have in really the near future. But before, one moment. I really skipped this. I don't know why. So before we go into technology, let's ask a simple question. Why is it so interesting to pursue autonomous driving? So if you Google this, if you are new to this and you Google this, you'll get some obvious answers, and I'll start with the obvious answers, and then I'll tell you something which is less obvious. Okay? So let's start with the obvious answers. So this is something I took from a Morgan Stanley report. So cars are the most underutilized, very, very expensive equipment that we have. It's utilized about 4% of the time. 96% of the time it's simply standing still in a parking lot. Okay? So we have here, I think it's the third expensive thing that we buy after buying an apartment and after paying for college. The third thing is buying a car, underutilized, and it's very unsafe. Right? We have in the US, about 35,000 fatalities a year. So it's kind of ready for disruption. Something here requires a disruption. So first, it's underutilized. Second thing is that if you look at shared mobility, like Uber and Lyft and so forth, the driver is 50% of the cost. So if you remove the driver out of the equation, all of a sudden shared mobility becomes a very economical enterprise. Right? Now, when you think about shared mobility without a driver and you have passengers in the car, then you can think about delivering content. This is why Silicon Valley is so interested in this. You have passengers in the car, maybe you have sensors that understand the mood of the passengers and what they're talking to each other, and you're starting to provide them appropriate content. Assume that you know that they're talking about coffee, so you can tell them, look, there's Pete's Coffee out there, and by the way, I get a cut from Pete if you go and drink coffee there. So providing content, data, it's all things that you can do once you have autonomous driving. So these are the obvious answers. You Google this is what you can find. The non-obvious answer is the following. There is a deep agreement and deep understanding that the future is going to be driven by artificial intelligence and robotics. The only problem is it's not clear what is the business model for artificial intelligence and robotics. So is chatbots a reason to invest billions of dollars? It's nice, chatbots, but is this the future? Is this worth spending so much money to develop? Look at robotics. Boston Dynamics. They make amazing robots. If you look at Google and then see those clips in YouTube, it's amazing technology. Yet it's not clear what to do with them. There are all sorts of military applications. It scares people. I heard. So it's true that the future is going to be driven by robotics and AI, but it's not clear exactly what is the crisp business model that will justify spending tens and hundreds of billions of dollars to develop it. But when you look at cars is an ideal platform for developing AI, because you have to have sensors feeding information into a computing device. That computing device needs to understand the visual field at close to human level perception. I'm not talking about broad human perception. It's more narrow, but still it's pretty close. So we need to develop AI that could drive a car autonomously, and then we're talking about sensors looking at passengers. We need to understand what the passengers are doing, their mood, what they're talking about. It's all AI. But here there's a crisp business model. Selling cars, shared mobility, shared ownership. At the last slide of this presentation, I'll go over all the disruptions that will happen if you have autonomy. So this is an ideal platform for developing AI. There's a crisp business model, and then once you developed AI, then you can go and apply it to other verticals. So this is why autonomy is so interesting. Okay? So I'll talk about, there are three ingredients, I call them pillars. There are three ingredients that are required in order to build an autonomous car. So I'll go, and some of them are not well defined. The well defined part is sensing. So sensing, you have cameras, you have radars, you have laser scanners, all this information is going into a computing chip, and you build an environmental model. Environmental model is tell me where all the moving objects are, where all the obstacles are, where the path delimiters are located, the curbs, the barriers, the guardrails, of course the traffic signs and traffic lights, and tell me where all the drivable paths are and their semantic meaning. Okay, so this is an environmental model. It's difficult, but at least it's well defined. The second pillar, mapping. You need very, very detailed map. Very, very detailed, not the navigation maps that we have today, maps that are very detailed, and they form a redundancy to sensing, because the camera will tell you where the drivable paths are, and if you locate yourself accurately in a very detailed map, you have also the drivable paths from the map. It also gives you foresight. Once you are on a path, you know where this path is heading to beyond sensing. So a map is critical. And it's not very well defined. I'll get to that later. So mapping is the second pillar. The third pillar is really not well defined. The third pillar, we call it driving policy. You can think about it as driving intelligence, or in robotics it will be called planning. It's kind of high-level planning. And to really get a crisp idea of what this means, ask yourself, why are we taking driving lessons? Think about it for a moment. Right? We're not taking driving lessons to train our sensing. By the age of 16, our sensing is as good as it will be. Right? We know how people look like, how cars look like. So it's not that. We're not taking driving lessons in order to learn how to control a car. With automatic gear shift, 10 minutes and you learn how to control a car. We're taking driving lessons because we need to learn how to merge into traffic. Why is that a problem? Because we are not the only agent. There are other agents out there, and those other agents, those other drivers, are not following the rules exactly. Right? If everybody would follow the rules exactly, it would be a simple problem, but they are not. Right? They are bending the rules, they are aggressive drivers, all sorts of behaviors that during driving lessons we learn them, and then we act appropriately. Right? We merge into traffic appropriately. Right? If we are the only agent that drives according to the rules, would never move. Right? So we have to know, when you are in Rome, you drive like in Rome. When you are in Israel, you drive like in Israel. Otherwise, you'll be dead. Okay. So this requires learning. Now, so we need to translate this to technology. What does that mean from a technological point of view? Because if our autonomous car is the only responsible agent out there, driving very, very conservatively, it will not work. Other humanly driven cars would be upset, right? So those are the three pillars, and let's put a bit more color and details to them. So first, the point that I'm making, that these three pillars are coupled together, they are intertwined. It's not three different areas, technological areas, that should be developed separately. They should be developed simultaneously. Because if you develop them separately, you start putting unreasonable demands on each of those technological elements. To give an idea of what does it mean, unreasonable demands, when we started the early 2000s, I knew that a monocular camera can detect vehicles, measure time to contact, warn against a collision, eventually brake before a collision, keep safe distance, and so forth. Now the industry thought that this is not possible. So I would go and meet customers, and I'll try to push this idea that give us the production for a monocular camera for doing these kinds of applications. And they say it's not possible. I tell them why it's not possible. They tell me, look, if you have a target 100 meters away, my radar sensor can get the range to that target at an accuracy of 20 centimeters. Can you do that? I tell them, of course, I cannot do that. But you, with your two eyes, when you drive, Can you tell whether a car is 100 meters away or 99.8 meters away? You cannot. It means that this kind of accuracy is not necessary. So this is what I mean by unreasonable demands. Right? So the same thing, if you treat sensing separately and you treat planning separately, the company that is doing planning will place unreasonable demands on the company doing sensing, and vice versa. So you have to treat this simultaneously. And the same thing for mapping. Okay, so let's talk about sensing. So sensing is the most well-defined problem, and let's start seeing what is challenging and what is not. What is really a leap that is needed to go forward, and what is an incremental growth of what we have today. So first, just a baseline. Of course, I'm here in a friendly crowd. Everybody here is about computer vision, but let's ask the question: why cameras first? Right? Because there are radars, there are laser scanners. For me, it's obvious. Maybe for most of you, it's obvious. But let's ask this question. So when you think about cameras, the first thing that comes in mind is resolution. And a camera is about 3 orders of magnitude more dense in terms of resolution than any other sensor, than radars, than laser scanners. And why resolution matters? You need details. In complicated scenarios like driving in a city, everything is about details. Now you can think of all sorts of tricks that allows you to have less details. Like, you build a very, very detailed 3D map and then you subtract it from sensing, but that, is a different opera, and it introduces other problems that I think are unsolvable. So you need details, and for this you need a camera. And another thing, that the camera is the only sensor that, in addition to shape, provides you appearance. All other sensors like radars and laser scanners are all about shape. A camera gives you texture, it gives you appearance. And since the world is built for humans that can see, there's lots and lots of texture information, like lane marks, like traffic signs, traffic lights, all sorts of cues that are texture-based and not shape-based. Therefore, a camera is really necessary. Without a camera, you cannot make this work reliably. Okay, so now let's go into what goes into an environmental model. So I told you that sensing goes into a computing chip and you build an environmental model. Now, I'll break it down into 3 elements. The first element is about moving and stationary objects. So today with driving assist, I didn't define what driving assist is because I imagine that intuitively you all understand what driving assist is. Driving assist is the technology to avoid accidents. So you have a camera facing forward, sometimes it's a camera and a radar facing forward, you detect pedestrians, you detect vehicles, you detect the lane marks, and you anticipate a collision and you send signals to the car control systems to actuate accordingly in order to avoid a collision. So that's driving assist. And driving assist, because it involves actuation of braking, false positives is something that you need to control very, very accurately, because you cannot afford driving leisurely and all of a sudden your car sees a shadow and thinks it's a vehicle and then automatically brakes. That's a catastrophe. It will cause a recall. So false positive really needs to be 0, but false negative, you can afford a certain level of false negative, right? When you're talking about autonomous driving, you have to have also false negative to be 0, and that you achieve by having redundancy, having more than one sensor look at the visual field. You need to detect vehicles kind of in a 3-dimensional box, 3-dimensional shape, and not just put a bounding box around a vehicle and say this is a vehicle or a pedestrian. You need more details, and I'll give you some examples. About pedestrians, you need more information about, it's not enough just to detect that there is a pedestrian there. You need to know what the pedestrian is doing. Is the pedestrian looking at me? Is the pedestrian on the road, on the sidewalk? Is the pedestrian, waving his hand? Is the cyclist waving his hand, and so forth? So more details about pedestrians and general obstacles. The point I want to make here is that all of this is easy. This is a natural growth of today's technology. There is no leap going on here. Continue doing what you're doing. If you are in the business of driving assist, you are detecting vehicles, you're detecting pedestrians, continue doing what you're doing and you'll get there. There's no leap. The second one, there's a small leap here, is path delimiters. So path delimiters, you want to know where the free space is, where I can drive where I cannot drive. So, and the boundary of the free space, tell me what is it? Is it a row of parked cars? Is it a curb? Is it a barrier? Is it a guardrail? Just tell me what is on my boundary of my free space. Right? This, I would say, is a certain leap above driving assist, but even that would be not that accurate because regulations of driving assist going to 2018, 2020 already include specifications of any boundary. So even without developing autonomous driving, just a continuation of driving assist will have by 2020, 2018, 2020, kind of any boundary type of specification. The real killer, the real difficulty comes with the drivable paths. So drivable path is not just detect the left and right lane. It's detect all the information on the road, all the drivable path, all the lane marks, and their semantic meaning. Is there going to be a split? Is there going to be a merge? Is this path is a highway exit? This path is going to merge 100 meters ahead. All the stuff that we take for granted, but it's very, very complicated. All the information about the road. Driving assist today is only tell me where the left and right lane are. Here we're talking about something much, much more extensive, and this is very, very complicated. I'll show you some examples just so that you appreciate the degree of complexity. And this is really a big leap. Okay? And this is only sensing. Why surround cameras? Because maybe I convinced you that you need a front-facing camera. That's really critical. You need to see the traffic signs, the road markings. But why not just simply have a front-facing camera, a radar, 4 corner radars, maybe a laser scanner in the front, laser scanner in the back. You have a 360-degree awareness, that's fine. That is true for highway. If you want just to enable autonomous driving on highways, this is called highly autonomous driving. It's coming out at around 2018, 2020. That's fine. You don't need cameras 360 degrees. But when you are moving into city traffic, you cannot afford to have an area of the visual field without the degree of details that the camera can provide. And I have here an explanation, but I'll skip that because of the nature of the crowd here. All of you are computer vision. You can figure that out yourself. So let's go over examples from the moving objects, from the path delimiters, and from the drivable paths, such that we get some idea about the complexity of what are the interesting problems to solve in these areas of sensing. Again, and then I'll say I'll mention a few things about deep learning and where they come to play here. So if you look at vehicles, the point I want to make here that when you go to autonomy, you need a lot of details about the target. It's not just that there is a vehicle there and you put a bounding box around it. You have to put kind of a 3D bounding box. And in this clip that I'm going to show you, now red is the rear, front is green, left is yellowish, and the right is blue. Let's run it and you'll see. So you can see that the system is when it's detecting a vehicle, it's putting a complete 3D bounding box around it. And this is exactly what you need when you're in complicated situations. So when you're driving on a highway, that is not necessary. Right? But when you're driving in city traffic, for example, this car on the right, the door can be opened all of a sudden. So you need to know that this is the side of a vehicle and exactly where are the boundaries of the side of a vehicle. Let me show you some more clips so that you can appreciate the complexity and why it is needed. So when you see an academic paper doing vehicle detection and putting a bounding box around a vehicle, that's not useful. Okay? You really need to figure out how to put a 3D bounding box around it, and that's tricky. That's tricky because this 3D bounding box is not always visible. Sometimes you see only the rear of the vehicle, sometimes you see only the side of the vehicle, sometimes you see both. Right? So when you think about the input-output relationship, say in a deep network, it's a bit tricky. Okay, let me show you a bit more. Okay, so you can see the need for something like this in complicated scenario. So the next time you read a paper about vehicle detection, bounding box around the vehicle, simply go to the next paper. Okay, it's really irrelevant. Okay. Okay, last clip here. Okay. Let's go to path delimiters and free space. Now, before I run this clip, I want to say a few words about deep learning. So now, deep learning now is really the tool. Deep networks is really the tool. When you think about what is really the breakthrough with deep learning, what I hear most people say is that the breakthrough is about feature engineering. It means as a computer vision practitioner, I don't need to engineer the features anymore. I don't need to think whether it's an LBP or whether hogs or whether sifts or these zoo of features that we had in the past. The network will learn it automatically. This is the big message. Well, this is not the big message. Because if you are a developer in a company and you are committed to a problem and you have the time, and in a company you have the time, then eventually you'll figure out what is the feature representation of the problem that you want to work with. Therefore, deep networks is not a groundbreaking. It enables you to do it faster. Maybe it will become more ubiquitous, but it's not transformative, because people can eventually find what is the feature representation of a particular problem they're working on, especially when it's important to work on that particular problem. So that is not really the breakthrough. The breakthrough is the ability to solve problems that you couldn't solve before. This is where the breakthrough comes. So now let's think about that. Back in 2011, 2012, my team came back to me and they told me, look, we think we reached a glass ceiling with the ability to do pedestrian detection. Now remember, before the age of deep networks, how would you do an object detection in an image? You'll have a classifier that takes a bounding box from the image and tells you whether it's a pedestrian or not a pedestrian, and you put all your smartness, all your cleverness into this machine learning black box. And then you had a kind of cascade sliding window that you're trying all possible locations and all possible aspect ratios and all possible sizes, scales, in order to scan the image cleverly, and this is you doing it the kind of the Viola-Jones cascade type of thing, in order to find the object. So this was the way, pre-deep learning. So they told me, we think we reached the glass ceiling. No matter what we do, and we had a very, very good pedestrian detection. 2010, it was launched in serious production by Volvo. It's something that worked. It's not, a research type of activity. But you want to improve. Today, pedestrian detection has a false positive once every 500,000 kilometers of driving, and has near zero false negative. Now this is serious technology. And they told us, look, we think we reached the glass ceiling. So the first thing we did, the first experiment, and I imagine that you would think about it right away, is let's take the errors and show them to humans. Let's see if humans do better. And lo and behold, humans don't do better. Because we really did the maximum that is possible from a bounding box. But because when you look at an image, you have also context. And this is what was missing. Harnessing context in the recognition. And this is what deep networks give you. Because with deep networks, you start with an image in the input. And what the network does also incorporates context. So in this example that I want to show you, it's all about context. So what I'm showing you now is a green carpet. And this green carpet is the free space. Okay? Now let's look at this clip, and I'll stop it at the point which is really amazing, and it shows why context here is being harnessed. Okay, so I'll run it slowly so that you can see here. So you see that the green carpet doesn't go on the curb, and the network understood that all of this is not road, only this is road. Okay, let's continue this. Okay. And let's stop here. See, the texture on the sidewalk and the texture on the road is really identical. No local, and no matter how big the receptive field is, no local detector would tell you that this is a road and this is not a road. They look simply identical. It is context that tells you that this part is really not part of the road. And this is something that would have been very difficult to achieve in pre-2012 era of computer vision. This is where the deep networks come into play in a very, very serious manner. So next I'm going to show you is what we call semantic free space. So it's not just the green carpet. At the edges of the green carpet there is coding whether it's a flat area, a step curb, a vertical curb, guardrail, a concrete barrier. We have about 15 different categories. Let's run this. So maybe I'll stop this here just that you see. So red means that it's an object, right? It's an object. And here you see this is a step curb, right? Let's run it a bit more. So all of this, by the way, is a single frame. It's done separately, frame by frame. And there are reasons why we want to do it single frame and not use continuity as part of it. Right. Let's go to some more examples so that you can get an idea. Okay, maybe if I stop this here so you can see. This here is a guardrail, right? You can see from here. And so so it knows it's a guardrail at the side. Right. And this you can see, this is in Japan. Right. So this is something that would have been almost impossible to do without the technology of deep networks. Let's see a bit more. This is when the road is wet, so it looks completely different when in normal daytime, and yet this network can generalize quite well. Okay, and this is, I'll stop it here so that you can see. Okay, so this sign here is flat. This is kind of here. So it knows that this is it's a flat boundary. Okay. So this is a semantic free space. Now let's go to the most difficult part of all is the drivable paths. And here it's not one algorithm. It's a fusion of many different algorithms, and I'll show you some of them. The first one is we call this holistic path prediction. So in driving assist, application of sensing lanes is for lane departure warning or lane keeping. So if there are no lane markings on the road, then it's okay. There's no lane departure warning signal to give. But if you want to control the steering wheel autonomously, then the fact that there are no lanes, what are you going to do? Are you all of a sudden going to ask the driver to take control immediately because it doesn't see lanes? That will not work. You need, because a human can see where the drivable paths are even if there are no lanes, right? We have kind of a virtual space, and we know how to carve this virtual space into those virtual drivable paths and drive correctly. So we want a computer to do that as well. So we need to figure out how to define drivable paths even when there are no lane marks. So this is kind of a Pomerleau type. If you recall the early 90s, there was this nice work from CMU. So this is very, very similar. You take input image, output, those three lines, the kind of left and right and center of the lane, and let's have a look at it. So even if there are no lane marks, this kind of network can correctly generalize and correctly predict where the path is. Show you some more examples, like something like this. Right? Clearly there are no lane marks, and this kind of network can generalize quite well, but it cannot end here. This is not sufficiently reliable to rely only on this output to navigate, because when there are lane marks, you want to use them explicitly in order to gain better accuracy. So it's kind of a system where you take also the semantic free space that I showed you before, you take this holistic path planning, you take the lane detection, other scene specific models, you put them together, you fuse them together and get a system. And let me show you some examples. So in this clip, what you should focus on is this short red line here, which is the fused center of the lane. And all the others are other cues that are feeding it. They may not be stable, but this red line is very, very stable. And what is really significant here is the difficulty of this scenario. It's not only that the road is wet, you're in a tunnel and there is backlight coming outside of the tunnel. This is really a killer for these type of processing, and you can see how stable this is. Right? So reaching these levels of performance requires going from the last 10% of performance, which is very, very difficult, requires pulling together many, many different algorithms that can work together. Here's another situation. Again, you don't see the lanes, yet this center, this red center, is dead on and very, very accurate and stable. So these are the building blocks in order to enable lateral control. Because lateral control should work all the time, even when the lane marks are not there or where the lane marks are not painted well and so forth. And also understanding the drivable path. So the system knows that there's only one path now, and in a moment there are 3 paths, and there's the probability of them. So it's kind of this is kind of a global perception, it's a holistic perception. Image in, semantic lane information out. Okay? So these again are building blocks that are put together in order to understand the road. And let's look about the semantic meaning of it. So when we look about road structure, there's lots of information about, we call these key points. Where is the lane split going to happen? When is the lane merge going to happen? Key information that allows you to understand the roadway. For example, here, this is a key point, right? There is here a lane split that you need to detect in order to infer the semantic meaning of the path ahead. So here again, these are networks, and it's a number of networks. For example, this network provides slope estimation. So the color is the slope. Okay. Now this is the ground truth, and this is what the network outputs, and you see that it's almost identical, right? And it's a complicated scenario. There is a split here of the lanes, because this is going to there are two paths here, and there's a split. Okay. Let's look here. This is what we call a complex lane, because this lane and this, so there was one road that is splitting into 2 roads, and the signals, the information that tells you about it is the fact that this lane here splits. So here it's color. When you have a blue lane, this is a simple lane mark, and this is a complex lane mark, the left and the right complex lane mark. And you can see that the ground truth versus what the network provides is almost identical. Let me show you something more interesting. Here you see quite let's look at this one. This is the ground truth, and the person who tagged, so we have today it's about 800 people annotating images. 800 people annotating images. Take an image and they annotate all the information that we need to feed into machine learning. Okay? So the person who annotated the image made here a mistake. He put this lane here, then the entire lane as a complex lane. What he should have done, or he should have done, is only mark this part as a complex lane, because this is a simple lane. And you see that the network, this is the output of the network. The network correctly made the right inference. This is a simple lane, and the complexity starts only here. So this kind of network is able to generalize over mistakes of ground truth. This is really a complicated one. This is complex lanes. This is from the ground truth. But there's another complication here that you hardly see, where the annotator missed and the network correctly infers it. Okay? So you can see kind of the complexity of things that needs to be handled. So I showed you here 2 things. One is estimate the slope of the lane. That was one network. Here's a network. Estimate whether detect whether we have simple lanes and complex lanes. Okay, okay, so that's what I want to say about sensing. Let's go to the additional 2 pillars. The next pillar is this merging into traffic. So in the first pillar, and why we need that, I said before, right? This is a kind of a picture I took down from the internet about today's experimental cars, which are driving too conservatively and upsetting other human-driven cars. And it's really a multi-agent game. You need to learn human driving behavior. So now, if we look at sensing versus planning, just to understand the complexity of the problem, when you talk about sensing, we're sensing the present. We're given an image or a video, and just tell me what I see around me. The fact that there is a neighboring car, for me it's an object, it's not a behavior. So it's sensing the present. It's a single agent game. I'm the only agent in this game. Right? And it's perfectly predictable. Give me enough input-output examples, I can train algorithms, I can train machine learning algorithms in order to do the correct mapping. And the technology is deep networks, deep learning. When you look at about planning, you are planning into the future. We are not the only agent. There are multiple agents here. And it's not perfectly predictable. And the technology is reinforcement learning. It's deep reinforcement learning. What you have in reinforcement learning, you have states and you have actions and you have rewards. And you're not optimizing the instantaneous rewards, you're optimizing the accumulative rewards. So say, for example, there's a highway exit 3 miles away and I'm starting to change lanes because the traffic is busy. When I'm changing lane, I'm getting a 0 reward. But the accumulation of those very, very small rewards is such that I want to know my success is whether I exit the highway smoothly, yes or not. So it's not the instantaneous rewards that matter, it's the accumulation of those rewards. And this is a big area in machine learning. I'll skip this slide. This is a paper that we released a few months ago showing that you can do deep reinforcement learning within a recurrent neural network and not using Q learning. Q learning, which is the popular way to go in reinforcement learning, assumes that there are many issues with it, but one of them, it assumes Markovian. It's okay to assume that I'm Markovian, but it's not okay to assume that the other players are Markovian. And this creates not an optimal environment. And this kind of algorithm, which uses recurrent neural networks as the basic element, doesn't assume Markovian, and it works very, very nice. Let me show you a small simulation. So in this clip, simulates merging into a roundabout. And the red car here is us. It's the host car, we are the agent. And there are 2 behaviors that the agent doesn't know about. The blue cars are aggressive drivers. Aggressive driver, when an aggressive driver sees you trying to squeeze in, he will accelerate. Okay? Imagine Boston, right? Imagine Israel, imagine, the green cars are more laid back. They see you try to squeeze in, they'll slow down. Now the red car doesn't know all about that, right? It's optimizing, making mistakes, optimizing, until implicitly it figures out that these are the 2 behaviors and you shouldn't squeeze in between two blue cars. Okay? And the way it looks is something like this. So you see how the blue car accelerates when, and the red car knows how to squeeze in appropriately. And there is a squeezing in process going on here. And this is something that is learnable. So it's roundabouts, it's 4-way stops. When there is a lane merge, you look at the other car beside you and you can try to estimate, should I speed up or should I slow down because there is a lane merge? These are all sorts of negotiations. When I change lane, it's also a negotiation. A 4-way stop, take a left in a 4-way stop. It's a major negotiation. All of this is learnable through real data and simulated data, and this is a big part of, it's a big pillar, big technological pillar. So let me, I'll skip these 2 slides because I want to go into the last one, which is mapping. So the last pillar, so we talked about sensing, we talked about planning. Right, the intelligence, the driving intelligence, how do I merge into and then all of these are stuff that we all do here. We all do machine learning, we all do computer vision, reinforcement learning, that there's lots of work on reinforcement learning. So all what I showed are stuff which are the core of things that we as a community do. The third one, mapping, is a very cool thing. So, and this is critical. Without it, you'll not have an autonomous car. So, sensing is well defined, right? We have cameras, radars, laser scanners, that's well defined. When you talk about mapping, that's a bit requires definition. We humans, we don't need a map, right? I can fly to Rome, rent a vehicle, drive. I don't need a map to allow me to drive. I need a map in order to know where to drive, but it's not that the map gives me the ability to drive. So if we're talking about artificial intelligence, why should artificial intelligence need something that we don't need? right? So we could possibly build an artificial intelligence, autonomously driven car without having maps, just having navigation maps to know where to drive. Yeah. So it could be no maps, just navigation maps, just to know where to drive. And then there's the high definition maps that, there's talk around it from companies like Here and TomTom, where they're talking about maps that are much more detailed than the maps today. And there's the Google 3D cloud of point. It's Google and the copycats following Google, right? So it's kind of 3D cloud of points, very, very dense cloud of point, which you can also consider it as a map. So when you talk about mapping, you need to decide where are you in this list. What complicates things is localization. If you don't have a map, you don't need to localize yourself. That's easy. If you have a navigation map, you need to localize yourself at an accuracy of a GPS, a few meters. That's fine. But if you have a high definition map and you want to use the map for control, this is the whole idea, to use the map for control as a redundancy for control, then you need to localize yourself at an accuracy of about 10 centimeters. Now, how do you do that? A GPS does not give you a 10 centimeter accuracy, especially not in city environment where you have blockage of buildings and so forth. So there's maybe in open areas, an RTK can give you maybe 10 centimeter accuracy. But in a dense city, drive in Manhattan, there's no way that you'll get a 10 centimeter accuracy from GPS technology. So it's not just that you need to define what you mean by a map, you need to solve the problem of localization. So these two come together. Having a high definition map without the ability to localize doesn't help you. So now, when we talk about maps, what are the requirements to enable autonomous driving? Now, it's a bit non-obvious, but once I show you that, it becomes very, very obvious. Right? Now here we're talking about maps, which it's a critical element. That means it's critical safety. Because without the map, you cannot do autonomous driving. You don't have redundancy, you don't have the foresight, so you cannot do autonomous driving. So if it's safety critical, it means that it has to be updated continuously. It has to be always true. Unlike navigation maps, which are updated once, I don't know when, once a year, once a quarter, here it has to be updated in near real time. So the conclusion that comes from it is because the map update should be a continuous process, it has to be crowdsourced. Meaning they have all the vehicles, you have 100 million vehicles produced a year, all of them should contribute information for updating maps. Okay? Now if it's crowdsourced, then we have bandwidth information because you have vehicles sending information to the cloud. Now you cannot start sending raw data. The infrastructure that we have, the 3G, LTE, 4G, they cannot support sending. So imagine millions of cars simultaneously sending, gigabytes of data. That would not work. So you need to think about bandwidth. So the data per kilometer in what I'm going to show you, which is based on pure computer vision, classical computer vision, not deep network stuff, classical computer vision, we're talking about 10 kilobytes per kilometer. So 10 kilobytes per kilometer is really nothing. If you drive 100 kilometers, it's about 1 megabyte. My smartphone, my Facebook app sends megabytes every minute. Right? That's 1 megabyte per day is really nothing. Okay, so you cannot send raw data. All the cleverness, all the intelligence should be on board because you somehow need to take the visual field that you see and extract from it meaningful information, which is about 10 kilobyte, and send it up to the cloud. And then in the cloud, it's being pieced together, and a map is being built and then updated. Another thing which is specific to the car industry, that cost is very, very important. Now, ideally, you want to achieve that without adding any new infrastructure, without adding any new hardware. So now there are two trends that are happening regardless of the desire to have autonomous vehicles. One of them is driving assist. Driving assist is being regulated. Regulatory bodies like NHTSA, like the Euro NCAP, are incentivizing car makers to put driving assist, to put a collision avoidance sensor in order to get their 4 and 5 stars rating. By 2020, every new car is having a front-facing camera to satisfy regulation. For example, Mobileye 2015 shipped 4.5 million chips, so 4.5 million cars. A year before it was half of that, the year before that it was half of that. This year it's supposed to be double. Okay, so it's all because of regulatory bodies involvement. So this is a trend that is happening regardless of autonomous. Every car has a front-facing camera and a powerful chip to process the visual data coming from it. A second trend is over-the-air update. This is something that began with Tesla, and the car industry is catching up. It's a very cool thing to have, that you can then update the firmware over the air, just like we do with our smartphones. And you can send data to the cloud, receive data. It opens up many possibilities. And the entire car industry, by 2018, are having over-the-air update. Okay? So these two trends, communication and a front-facing camera in the car, are happening regardless. So now, ideally, all what you want to do is add software to the front-facing camera. That's it. No new hardware, nothing. Okay? And this you can do through computer vision. So what is the idea? The idea is to treat the three-dimensional space. So this is kind of, it's a variation on SLAM. But it's a bit more clever, because SLAM is heavy in terms of data. So think about 3D as composed of sparse elements, which are landmarks. What are these landmarks? Traffic signs, traffic lights, poles, reflectors, anything static in the scene. In the next slide, I'll show you a list. Okay? So this is, I call this sparse 3D. And then the information that you want to harvest are the lane marks. The lane marks, the path delimiters, all the stuff that comprise an environmental model facing forward. And this is dense, but only 1D. So it doesn't take much of data. It's only one-dimensional data. Therefore, if you put this together, it's about 10 kilobytes per kilometer. This you send, okay, so here's an example. So just a example, it's about, we have 20,000 different landmarks. So it's a vocabulary of 20,000 different objects, but this is just showing you some of them, also poles, reflectors, bridges, tunnels, anything that is fixed is a landmark, and computer vision can detect them. Okay. Here it's just a road in Germany. Just you see the density of the landmarks, like the pavement markings is also landmarks. Okay. Now, if you go and measure what is the worst case separation between two landmarks. So the worst case would be on highways, right? In city is dense with landmarks on highways. The worst case, if you go over the entire US, the worst case is 200 meters between two landmarks. So if it's 200 meters between two landmarks, what is the next idea? The next idea is you use your ego motion. Use your ego motion in order to continue your positioning. And the ego motion at some point will start drifting. And you want to make sure that when those 200 meters you don't drift. Or you drift at most 10 centimeters. And ego motion, we all know in this community, is something that has evolved through a long period of time and is now very accurate. Okay? So with ego motion, landmarks in order to correct drifting, right, and all this 10 kilobytes, you can start building these maps. Okay, so let me. So this is the clip here shows the harvesting. So what you see here as the lane information being pieced together using ego motion. Okay, and this is being sent to the cloud. And in addition, the system detects and recognizes landmarks. So let me show you some examples of this. This is ego motion, the nice and old ego motion. So here what is being compared is ego motion compared to a $30,000 inertial sensor. So a very accurate inertial sensor. And you can see that ego motion today has reached a technological position which is very accurate. And all what we need is 200 meters accuracy, because then we get the next landmark. And the worst case, normally it's every 10-20 meters you have a landmark. Okay, so we call this map a roadbook. What does it give you? It gives you a localization at an accuracy of 10 centimeters. It gives you a high definition map content, because we have all the elements of an environmental model, all the lanes and the semantic meaning associated with them. And then you can actuate control using the map content. So it's sufficiently accurate that you control the car. After you localize yourself in the map, you can control the car. This gives you redundancy. So let's see some examples. So in this example, we see localization. This point is moving in the map being built by this technology. We call this technology REM. road experience management. The word stuck, I don't know, it's nonsensical, road experience management, but it's stuck there and that's it. Okay, so this is the localization. Let's see here. So this is, one moment, let me go back. Okay, what I'm showing here, this is not lane sensing. This is projection from the map back to the image coordinates. And it's so good that you think that this is sensing, because you see the lines are sitting exactly on the lanes. Okay, so this shows the accuracy of the map. Let me show you a bit more. This is a test done by Nissan back in January. So this is autonomously driving in San Jose area. So in city traffic, and what the output is these 3 control points. At the end, when you wanted to control, this is what you need to provide. The control points where the car should be in 0.8 seconds, 1.1 seconds, 1.3 seconds, something like that. And when we look at this, you can see, for example, here we're taking a right turn, which had been very difficult to do because you don't see lanes. Sensing would be difficult to rely just on sensing taking this right turn because you don't have enough information from sensing to tell you exactly where the path is. This is where the map is useful, and you see how accurately this turn was made. Let me show you another one in Tokyo. What was the length of it? 20-kilometer urban driving, all hands-free. And here you can look at this just to get an idea. Again, there are 3 points here that you hardly see, but you can see how urban this is. This is really urban type of driving, hands-free driving. And this was a stretch of 20 kilometers hands-free completely. Okay, and this map, this REM technology is critical in order to fill in the gaps where sensing becomes ambiguous. Here is a test being done with the Volkswagen, taking areas, complicated areas like this, and mapping them. So see how many lanes there are here and the complexity. For example, here, this is a stretch of 28 kilometers being mapped, and this is the projection on Google Maps. So you see that these lines are projected on the Google Maps. It already tells you that there's an accuracy of a few tens of centimeters, because otherwise you'll see the colored lines not aligned with the lanes on the Google map. So this already tells you we are an accuracy of a few tens of centimeters globally. Here's also an example of projection. So this is not sensing, this is projection. And let's have a look at it. You can clearly see it's a projection because these purple lines are crossing an obstruction, an occlusion. But later you'll see that these purple lines are really sitting on lanes. And this tells you, gives you a sense of accuracy of this system here. You start seeing that this purple line is sitting on a lane. Okay. Again, we need to reach 10 centimeter accuracy. Now this is clearly projection, because you'll see this again in a moment, because you'll see that the lanes are curving way beyond the sensing. So this is a projection from the map, and this is kind of the complex area that is being mapped. This is a proof of concept with the General Motors, again taking areas, and let me see here. You can see again this is a projection because you see this line is crossing through an occlusion. And this is the projection on Google Maps. So you can see really the accuracy is a few tens of centimeters. Otherwise, the lines would have been shifted. Okay. Let me see another one. The same thing here, and you can see how it curves. So it's a projection. So these are preparations for the technology to be launched somewhere in 2017. We'll start building the maps, such that by 2018-19 we'll have a worldwide index where the entire car industry would be contributing information for these maps. Today we have GM, Volkswagen, Nissan, BMW already joined in, and by the end of the year I believe that we'll have most of the car industry inside this program. So imagine by 2020 all new cars that are being manufactured have a front-facing camera, and all of them send data for this kind of mapping. Okay, so this is the last slide. Let's summarize this. So we are in 2016. So the years 2015, 2017, we have what is called highway autopiloting. For example, the Tesla autopilot. This is not autonomous driving. This is unsafe lateral control. Right? It's unsafe because it can make mistakes. And naive people, when they see something works 95% of the time, they feel it works 100% of the time, and they can make stupid mistakes. So this is not autonomous driving. What would be coming, and this is our technology as well, right? What is coming 2018, 2020 is what is called highly autonomous driving, where you have really 360-degree awareness, actuation only on highways. So if you're out of a highway, you cannot activate it. It's only on highways. But then you get a grace period of about 30 seconds to take over. So this is really safe. You can really disengage from the driving experience, read a book, even go to sleep. If the car needs you, it will wake you up. And if you don't wake up, the car would slow down and move away and stop someplace. Okay, so it is designed so that within highway driving, it is completely safe. And this is coming by the car industry somewhere 2018, 2020. The real jump is what is called fully autonomous driving. It's called level 4 or level 5 autonomy. And this is coming 2021. And this is for ride sharing. So these are fleets, not sold to the public. These are fleets. They operate in geofenced areas. And the purpose here is to build new business models like Uber, but without a driver. And the car industry is now moving forward to become a serious player in that area. You hear about GM investing in Lyft and so forth, Volkswagen and Get Taxi. And it's all preparation for 2021 for the car industry, and we are a central player there. Introducing 2021 fully autonomous driving. I'm not talking about regulatory bodies. I'm not talking about that. I'm talking about technology. Technology 2021, you can have cars driving fully autonomously. I speculate that from a regulatory point of view, you'll have to have someone behind the steering wheel for the few years in order to gain confidence, in order to gain statistics that these things are safe. And then only when society has enough statistics that these cars are really safe, then a driver can be out of the driving loop. 2000 and above, after 2023, once you have, especially if you buy into this mapping technology, which allows you crowdsourcing, so mapping is done everywhere simultaneously, you can go from geofenced area to everywhere. And now we are talking about even a stronger business model, not only of shared ride sharing, but shared ownership. It means I have a car, I can drive my car to work, whether I drive it or the car drives me, doesn't matter. I take my car to work and then I send it back home. I can be in New York, I go to Boston, from Boston to New York, the car goes autonomously back home. Gets home, does what it does, takes my children, my spouse, whatever, to wherever they need to go. In the evening, it comes back and picks me up. So you can see that one car has a much higher utility, therefore you need less cars. Also, the ownership model can change. It's not only one household doesn't need 2 or 3 cars. It could be several households would share a car, or something completely different. Instead of me owning a car and replacing that car every few years, I can pay a monthly subscription, say, to Audi. And then, based on my mood and my needs, today I'll order an Audi Q7, which will come autonomously to me. I use it, send it back autonomously. Next day I'll order an Audi A7, and so forth. And all what I need to do is pay a monthly subscription. So you can think that business models would completely be disrupted and change when you have this kind of ability. So it comes in 3 steps. One is highly autonomous driving, which is a cool feature to have. You can drive autonomously on highways. It's a very nice feature to have. It's not transformative. The 2 transformative stages are starting from 2021. One is for shared mobility, Uber but without a driver. That's a big transformation. And the real kicker is when cars can drive anywhere autonomously, and this is where ownership changes, models changes. The entire transportation as we know it will change completely. And 2021 in the automotive era is really around the corner. Okay. So I think I'll end here, and if there are any questions, I'll be happy to answer. Thank you.